What's up, everyone? This is The Bridge. I'm Jeff.
And I'm Adrian. And today, we're here with Student Space Systems.
Wait, what? What are we doing today?
We're about to interview Student Space Systems.
I don't know what they are, who they are.
Okay, Student Space Systems is this awesome, high-powered rocketry organization here at University of Illinois.
Okay.
Their goal is to push the boundaries of what's possible for student rocketry organizations. One of the ways they're pushing the boundaries is by making this liquid rocket that they're planning to send past the Kármán line. Do you know what the Kármán line is?
I really don't know.
Okay, so the Kármán line is 100 kilometers above sea level, and if you surpass it, you've been considered being in space.
What's the point, though?
Well, if you're able to pass the Kármán line and actually develop like a vehicle that is able to go that far, you're able to send experimental satellites and work with companies. Real companies like SpaceX or NASA even could fund your missions.
But the thing is, I'm in material science and engineering. I don't know what I'm doing with SSS.
Well, even material scientists have a huge part of building a rocket. They have to develop all the materials like carbon fiber and fiberglass. There you go.
That's awesome.
You're getting it.
Let's go check this out.
For sure, dude. Today we're here with Ben. Ben, could you go ahead and just introduce yourself and tell us what you used to do at Student Space Systems?
Sure, my name is I'm a 2017 of University of Illinois Aerospace Engineering Department.
My name is Florin Gannett, and I'm a co-founder and former director of propulsion for Student Space Systems.
My name is Nick Schwengler. I'm a junior in aerospace engineering at the University of Illinois, and I'm the administrative president for Student Space Systems.
I'm Joshua Super. I'm the director for the External Relations Department, SSS, and I'm an aerospace engineer.
Hi, I'm Caitlin Benva, and I'm working on V1 integration.
Hi, I'm Luke Smith. I'm the director of Avionics.
I'm Miles McKegg. I am the director of propulsion for Student Space Systems.
My name's Griffin. I'm director of structures for Student Space Systems, and I'm a senior in aerospace engineering.
My name's Grayson Scher. Been a member of the club for 3 years now. I started the second year, and right now I am a subject matter expert.
Hi, my name is Varun Bhargava. I am a sophomore in aerospace engineering here at the University of Illinois, and I also minor in computer science. I am Student Space Systems Research and Development Director for this year, and I'm really happy to have the opportunity to speak to you guys about SSS.
So Student Space System is a group of students from the University of Illinois, and we design and launch extremely high-powered rockets. So currently we have designed and are building and manufacturing and testing a liquid rocket engine. It's the first liquid rocket engine ever launched from the university, and hopefully then be able to move on to developing liquid engines that can be used in rockets and eventually reach the Kármán line and outer space. There are a few schools who have been able to get liquids. I think 2 other schools have been able to develop liquid engines. I don't think any of them have ever flown in a rocket, but we're certainly on the forefront of actually developing student-designed liquid rocket engines.
What other projects in SSS were you previously involved in?
Probably all of them. Everything from all the main phase rockets, phase 1, phase 2, and phase 3, with all the propulsion projects, including engines, and then also structures. So putting together level 1 rockets, putting together designs for experimental rockets, working on TVC, thrust vector control. For a time I was part of Avionics, did some stuff there. I've been pretty much all over the place as kind of a subject matter expert in whatever areas that I know.
In 2013, I founded Student Space Systems with 4 of my friends, and I was the technical president for the first 3 years, managing the technical engineering projects of the club, and also helped with various funding proposals and kind of generally the whole overall path and vision for the club.
So when I joined SSS my freshman year, I joined the Turbopump electronics team, where we were working on developing an inverter for a pump driven by an large electric motor. I also joined the CO2 pneumatics team, where we're working on investigating the feasibility of using small 16-gram CO2 cartridges in the rocket to power small pneumatic systems, like opening doors or something. And I also joined the Level 1 team, where we built and launched a small model rocket to gain Level 1 certification with the National Association of Rocketry. Then sophomore year, I stuck with Turbopump Electronics team and also worked with the Turbopump team developing the impeller, so the actual geometry pumping the fluid. And now I mostly just work with the team developing the impeller.
So I started out in SSS on the Turbo Electronics team, and basically we are in charge of working on the electronics and power delivery to an electric motor that's going to be spinning the fuel pump for our rocket.
I've been involved in integration since my freshman year, when it wasn't called that, it was just plumbing. It's kind of graduated.
Why is it called plumbing?
It's just a glorified plumbing system.
You've been promoted to the position of technical director.
Yeah.
So could you talk a little bit about that and some of the challenges that come with that position?
So technical director, technical president is like the person that oversees all 4 of our departments. You don't necessarily have to be technically skilled in all those. I definitely am not the master of avionics, propulsion, structures, and now research and development, but you just kind of have to be able to coordinate a lot of projects kind of between every department. Sometimes people get stuck and they don't know who to talk to, and I think I'm kind of an approachable person that can send you in the right direction.
I have mostly been involved in, always in propulsion. In fact, for the most part, I've been working on injector. For both V1 and V2, I was heavily involved in the V1 design, and I sort of laid the groundwork for what would become V2, including the software that we used to actually design the system.
So I started off on a team called Flight Simulation, where we worked in CFD and FEA, and then eventually I worked towards tanks or engine integration, and then I became project manager of that, and then ended up now being director of structures.
There's 2 subsets for this. The first one was the project that I worked on during the entirety of my freshman year. So that was the actuating fin system research project that's in the Department of Structures. I had a team of 5 people as a project manager. It was a great experience. The project is continuing. We are essentially trying to find a great solution for future SSS rockets for controlling, at least initially, the roll around the z-axis of the rocket.
So this is my 3rd year in SSS. My freshman year, I was the project manager for our liquid engine test stand, so designing and developing the test stand for holding down the rocket and taking all the measurements that we needed. My sophomore year, I worked as the external director, so in that position I kind of handled corporate and university relations for the club, and kind of building on top of that administrative experience, I then became administrative president, which is my current role. So now I kind of organize the club, help make sure things are running smoothly, make any organizational changes that we need, and then also still deal with corporate and university relations and things like that.
My first ever project with SSS was telemetry, visualization, and collection. That was when we just developed a front-end kind of program that displayed live telemetry results from the rocket onto a dynamic web page. I left that after about a semester because I found something else called state estimation, which is basically when you're flying a rocket, you can't have sensors that measure everything on the rocket, so you can't fully define the state of the rocket. Like you can't know perfectly your altitude or your acceleration because there's noise and there's a lack of sensors.
So you can't really do Tesla's self-driving car concept on a rocket.
You can. Actually, that's where state estimation comes in. State estimation just uses a specific form of control theory, and actually state space interpolation, but it allows you to estimate the state of a system using a minimum number of sensors and it closes the amount of error in your estimation over time. So it's actually a really cool process.
It's like a self-flying rocket then.
Kind of, yeah, kind of. It's like if you've got a rocket and all you have is accelerometer data and altitude data,
right,
it can kind of interpolate that data over time and tell you what direction you're pointing.
It's still in development though, this technique. It's
So
not really mature.
It's in development for SSS, but it's well defined elsewhere in other forms of industry. It's actually the only way to control a rocket in actual industry, because you can't put just infinite number of sensors on your rocket. You know, you can know how much thrust you're producing, but you can't know the exact direction that your thrust is exiting the rocket. Or you can know what your acceleration is, but you can't effectively measure your exact velocity, just because of the way incompressibility and compressibility shifts as you fly and the dynamic changes in the pressure of the atmosphere.
Starting off, like, obviously is never easy for any founder, and since there were only 4 of you, I'm sure there was like a lot of work to go around. What was kind of your guys' approach to founding the club?
Well, so our first few months of undergraduate school was everyone tells you need to get involved. You need to get involved in projects. That's kind of how you learn outside the classroom. And we all tried that. And when you're a freshman, you kind of are naive to how much work you're actually going to have in college. And so we all joined maybe 7, 8 different projects, which
totally relate.
And so we were in that, and then after a couple months passed, we realized not much was happening. And it just felt sluggish, and projects that should have been fairly quick should have been, had made progress by then. And so, and in addition, as freshmen, we didn't really feel like we were being taken seriously. People would be somewhat condescending to us. There was only a few jobs for freshmen in clubs at that point, and a lot of the jobs were just kind of, placeholders and just for the name. And so, myself, when we were in, CAD class teaching NX8, I think it was at that point, I had watched a project. I'd seen a launch from a project from a rocket called Quake, QU8K, I think. And I went to 120,000 feet, and I was thinking, why don't we do a project like that? Because none of the student groups were doing that at that point. USC had a team like that. Delft had a team like that, and there's a bunch of other colleges. MIT has a team like that now. And so our approach was, one, we wanted to make sure freshmen, were cared about and were valued, because although you don't know as much per se, you can still gain that experience. And even in today's world, it's not necessarily based on your degree, but it's like how much you know and what your skills are.
Right.
And so just because you're fresh out of high school doesn't mean you don't have any skills. So that was our big one. Second one was we wanted to make sure stuff got done, and that our money didn't go into things that like bar crawl. If we wanted to accomplish the goal of sending a student-built rocket to space, spending $2,000 for an open tab isn't the idea of money well spent. We wanted it to be somewhat a facsimile of what a real company would feel like, so that when students graduate in addition to internships, they kind of have that feel of accountability and responsibility.
When you started the club, there were obviously a lot of expectations you had, but now today, like, the club has grown so much, it changed a lot. And the reality might be a little bit different. Could you talk a little bit about that expectations versus reality?
Yes. It's a tough question because thinking back, we didn't really know what it was going to turn into. The first year was all foundation building, setting up departments, setting up projects, setting up bylaws. Like, we try to make it such that the footing that the club was going to be on would be really strong, such that like everything would still apply 5 or 10 years down the line. And that's really the timeline that we were thinking was like, maybe we'd be lucky. We had this like timeline 2022 or 2024 that was like, that's when we'll do the space shot or get close to doing something like that. And we didn't really know how many people were going to join. And then the big surprise was sophomore year when we went on quad day and we first advertised the club publicly, and we had like 400 signups in one day. And we were like, we're unprepared. Not unprepared, to deal with all those people, but really to, do we have enough things to do? Do we enough work for people? Do we set up enough like educational like library in a sense to get everyone involved. But I don't know, I think it all worked out in the end.
So like, why do you choose to work on those projects?
Sure. Well, I mean, it's cool, right? I mean, who wouldn't want to do things that some people might see as almost impossible, or some of the most challenging things you could do during your time as an undergrad student or something? When you go somewhere and see like a massive rocket or something really powerful, like a large engine, it's impressive, and it's something that you want to be a part of, and something that you would want to work on. And I think also just a part of taking on massive challenges that seem almost undoable, but then figuring out a way to do them and working with other brilliant people to overcome that challenge and see what it takes to accomplish your goals. Obviously, nobody can do what we're doing by themselves. You need a large team. I think we have about 80 active members in SSS right now, and we couldn't do it without all of them.
We are currently on the cusp of firing our first liquid rocket engine, which is a huge step. Very few groups, especially student groups in the country or even across the world, have achieved that step. So the work we're doing is incredible. On top of that, we are working to go further beyond that. We are on track to implement a turbopump, an electric turbopump in our next engine, which, should it succeed, puts us in a class really outside of any other student organization anywhere in the world. No one attempts turbopumps unless you have literally thousands or millions of dollars. It's not easy to do, and having a group of students doing it is incredible.
So is it just the difficulty or also the price that typically prevents groups from doing it?
There's a lot to it. The main problem is traditionally manufacturing these components. Turbopump impellers are complex pieces of flow geometry, and you can't just, pull out a 3-axis mill and mill down a chunk of steel. You've got to get a full 6-axis mill with huge ranges of motion and carve very intricate patterns with high tolerances. And most of the way we're doing it now is by 3D printing, because it removes a lot of the difficulty. But even then, just the software to be able to be certain that this impeller works compared to other systems is huge. And on top of that, it's only finally becoming possible to realistically implement an electric turbopump, with Rocket Lab having done it most recently on their Electron rocket, which is a huge achievement. It's just the technology has never been mature enough. So designing a turbopump up until recently was not just designing an impeller, it was also designing a turbine. And that's a complicated problem on its own. Entire branches of engine manufacturing companies for aircraft are dedicated to making turbines. But you also have a whole separate engine inside of your engine called the preburner, where you've got another injector plate and another ignition system, and it's all being guided to that turbine. And how do you then use that exhaust gas? There's so many questions that just make it a massive engineering hurdle that isn't really achievable by most student groups, and much less just groups in general.
How will the turbopump enhance future SSS designs?
So there are 2 ways to pressurize the fuel going into a rocket. One way is to have huge tanks of high-pressure inert gas upstream of the fuel and oxidizer, which is what the first engine for SSS is going to be doing, but that's pretty heavy and not super efficient. So what most rockets will do is they'll have a pump and a low-pressure fuel source. So the pump will increase the pressure as it heads towards the rocket engine. So what we're doing is developing a pump that will function in that way for a future rocket in SSS. Almost all of the design comes from online resources, textbooks, and anybody in the industry we can talk to. We reach out to professors occasionally and ask for advice on anywhere from simulation to experiment design. So we try to gather as many outside resources as possible, because on a critical piece of engineering like this, it's good to have people with a lot of experience as well. I know a lot of the online resources, for example, in the first section, they'll mention that the quality and the efficiency of a turbopump is almost directly correlated with the experience of the designer. So without any experience, we're hoping to garner that from outside resources.
So you talked a little bit about creating tanks. Could you talk a little bit more about those tanks in your design work?
Yeah, so main difficulty is the pressure considerations, as well as the modularity of the system. So we need to contain the fuel and the oxidizer for the rocket. We need to do it in a way that's somewhat affordable, light, which is extremely difficult, and it needs to be sealed. So there's going to be O-rings. There needs to be a perfect seal. So that's pretty difficult without really good manufacturing methods. Some companies will use carbon fiber now. We can't make a carbon fiber tank. That's pretty difficult. There's a lot of design considerations, and mainly the thing is it's a mission critical system, so the fidelity of the design needs to be very, very high, and that also makes it difficult. If it doesn't work, the thing blows up, and that's not an understatement. So a lot of responsibility, and in testing for test tanks, if it blows up, people could get hurt. Keeping that in mind, especially at the undergraduate level, having those requirements it can be pretty difficult. We have the test tanks done, but the flight tanks are still ongoing. And the biggest thing is we can do it with a lot of money, but it's about balancing cost with the design.
What specifically about the design work and the work that Avionics is doing is so crucial in SSS's rocket?
Well, basically without any sort of avionics, it'll, for example, for a liquid rocket engine, you'll have all the plumbing there, but it can't do anything because there's no way to open any valves. There's no way to get the fuel flowing. There's no way to trigger the ignition. There are some really old school techniques that I'm sure they did before they used a lot of computers, but basically it's almost impossible to coordinate all these systems working together without some sort of brain, so to speak, calling the shots.
What do you think is special about this R&D?
I think R&D is a vital function for a club like ours. And the reason is that we're really trying to move away from things like pre-built. And that is why our current project, we're doing everything pretty much in-house, including design from the ground up. Sure, some complicated things are machined out or contracted out, but in general, everything is from the ground up. And it's something that's unique. Not a lot of colleges and clubs do this. I think R&D is a natural fit for a club like ours, who's always trying to innovate. We want to move forward. We want to break into new dimensions. And we want to seriously just take this club forward. And in that respect, I think R&D is a great way to help our members get that experience that they need to get comfortable with the entire process of research and development, and also provide some valuable technologies in the future for rockets that SSS develops.
You've had so many different work experiences that obviously a lot of different skills have been developed. Yeah. But which of those skills do you think is going to be the most beneficial to you in other areas of your life and further on in your career?
Oh, that's tough. I don't know if there's only one. I'll give you the big three, right? Okay. Yes. At the top is teamwork and communication, because they go hand in hand. You need to know how to work on a team with other people and know how to communicate your ideas or problems or your work, or even, I know there were times where I had problems writing emails because I didn't know how to write emails properly, and I would write paragraphs to professors and be surprised when they didn't respond, right? So it's learning how to communicate is key to being an engineer, and then working on a team. Alongside that, you need to be able to interact with people. You need to know when to compromise. You need to know when to take their ideas and combine it with yours, and it's all a big mushing circle. But those I would say teamwork, communication are the big ones that are required, because anywhere you go work in industry, you're going to be on a team. You're not going to be the only engineer doing one project by yourself. That's not going to happen. And then the second one would be, honestly, reading. A lot of engineers don't read enough. And that's kind of how we got off the ground. Was we spent the first couple of years, especially in propulsion, reading. We read probably every propulsion book there's ever been written on liquids and hybrids and all those things. That was the only way we knew how to design these systems, is by reading what's available, what documentation is available. And I feel like a lot of engineers are too quick to, I'll jump to that chapter, extract that really quick equation that I need, but not understand everything that came before it. Or what's the foundation for the equations you're using, or do they actually apply to your system? You know, so it's a lot of people are too quick to try and solve their problem as quick as they can and not realize they're going down the wrong road until it's too late. So if you do proper research before that, you save yourself trouble down the line.
Could you quickly explain for the audience what RDFL is?
Rocket Design and Fabrication Laboratory. It's basically where, like our own lab, where we do stuff. Has some machines, some soldering stuff. We keep a lot of our materials there. We do assembly there, and mainly the biggest thing is it has a computer with a lot of software that we use. Professional grade ANSYS software as well as CAD and other stuff. So we do a lot of simulations and stuff on that computer. We made a lot of changes over the last year. One of the biggest things being the meetings are all uniform. So if I want to go talk to a propulsion person, I can just walk over there. I can go see what they're doing on the whiteboard. It's very easy for me to do that.
How do you go about in such a large department like Avionics?
So basically, over the summer, I just sat down and tried to draw the whole goal of avionics and all of the systems that we need to create just from scratch, just to determine what's the minimum we need to make this work, and then work from there. It's easy to just get overwhelmed with how many things you can do and how complicated avionics can be. So basically I thought of that from the ground up, and then really just came up with about 5 core teams. Just making that clear from the start makes it a lot easier to manage a large team of people, because then, you know, hopefully everyone's on the same page.
The entire SSS rocket costs a lot to build. So how does SSS go about getting some of these costs covered?
Some of our funding comes from corporate sponsorships. We have sponsorships from a variety of companies that you can see on our website. Corporate sponsorships make up a large portion, but we also have funding from the Illinois NASA Space Grant Consortium, as well as some university sources, including SORF and the Student Sustainability Council. As we transition to liquid-fueled rockets, the cost of the rocket is increasing, just as the complexity does. Looking at just the engine, for instance, we're talking about tens of thousands of dollars. One specific component of the engine, the injector plate, cost upwards of $5,000, and that's just one component, for example, so probably upwards of $30,000.
So we're no longer dealing with just model rockets. This is like serious stuff. This is like the same stuff that NASA is working with, right?
Yeah, so we're not dealing with model rockets anymore. This is real engineering. All of the components, or as many as possible, are designed and built in-house. So this is real engineering, not so much model rockets anymore.
What is it like to be a woman in engineering?
Rare. I think I'd start off by saying it's not as rare as some people would think. Being a non-engineer, you probably think it's just me and like 3,000 guys in a single classroom. There are a pretty fair amount of women, especially in my major, mechanical. And the best thing about it is, you know, we're treated equally. We don't go into those stereotypes where the girls separate themselves. I think we bring a lot to the table, just like underclassmen do or upperclassmen. We know a lot more things that you wouldn't necessarily expect.
What do you think is special about Student Space Systems after being in the club for 2.5 years?
I think it's especially cool that we have so many people from different majors coming in. I think I've been in a lot of clubs where it was just mechanical engineers or it was just aerospace majors, but in Student Space Systems, like I said, we've had like history majors. We've had people that just their passion is rocketry. And it doesn't just have to be engineers. I mean, I've met a lot of people that are computer science, electrical engineering, mechanical, aerospace, someone from everywhere, and everyone can join Student Space Systems. You can be a freshman and we'll teach you everything you need to know. And I just think that's really special. I think that having people at not only different skill sets, but different times in their education. So freshmen coming in, I think that they bring things to the table you don't expect them to. Like I've met freshmen who have had thousands of hours in Kerbal Space Program, and they're not an aerospace major, they're ECE, and they know more than someone who is an aerospace major. And so bringing all these different skill sets into one place is really important.
Probably the coolest thing that I've done, or I think the coolest part of my part of SSS, is being able to come in as a freshman, completely fresh out of high school, and being trusted with the responsibility of designing and then making a test stand to hold a powerful liquid rocket engine. I can't imagine any other club that would take a freshman and give them that amount of responsibility. And of course there was oversight, making sure that I didn't mess up the design or anything like that. And that I went through the proper safety precautions and whatnot, but there's very few places at university campuses where you can get that much responsibility immediately as soon as you join a club. I think that's really kind of the coolest thing, is I was able to have that experience as a freshman, and that's one of the goals that I try to always succeed at as an administrative president and as external director too, is just making sure that that opportunity is available for every member at SSS. So we never discriminate on people just based off of their year in school or anything like that, and that the job, if you are able to handle it, will be given to you.
I think it's really special when you afford young engineers that are just getting into it the opportunity not only to utilize, flex some of their newly formed mechanical skills, design skills, but also give them a taste of what the management approach in engineering is like. At SSS, we've always tried to take an approach to management structure, scheduling structure, cost estimation structure that mirrors industry. We try to go through proposals and SRRs, PDRs, CDRs. We have all these reviews that we go through to make sure that we're taking the right steps. And I think it's something really special that trains these guys what industry is actually going to be like and what steps it takes when you have this big complex system and 100 people working on it. You know, it's not just one person designing it. You have to have a lot of interplay between the different sub-teams, and the way that you get those subsystems to interact is based exclusively on your management philosophy. So,
considering these huge steps that SSS is already taking, where do you see SSS in the next 10 years?
So our long-term goal is to create a launch vehicle for suborbital launches that universities can purchase flights on at cost of fuel alone. The main steps to achieving that right now are we are working on our V2 engine. It's a more powerful engine than what we've currently got, about 3 times more thrust with more efficient fuels, and designed from the ground up to be integrated into a flight vehicle. Our current engine, the plumbing is massive. It requires giant plywood boards to keep it all in place. We can't fit it in a rocket. But with our next engine, with turbopumps and with more compact plumbing, we're hoping that we can solve that problem. If we can do that, then we're on track to launch above the Kármán line in maybe 5 years. Beyond that, it's developing a vehicle that is actually viable for universities, where we can actually offer launch services. We can recover the vehicle and we can reuse the engine and all these things to go from a technological proof of concept to a service we can actually offer as a launch provider for universities.
How does that feel from your perspective to go from just launching these amateur rockets to potentially having the group you founded be the first group to go liquid with a liquid rocket into space?
It would be pretty amazing, to be honest. I mean, I was in Lincoln Avenue residence hall my freshman year. And so I remember our first meetings were held, if you went in that door to the right, there's some conference rooms. So our first meetings were held there. And so going from remembering what that was like in the meeting of 5 to 8 of us and imagining what our club would become, to having, the RDFL labs 1 and 2, having the new 18As, because those weren't there my freshman year. They just had Putnam's office. That office was the club office when I was a freshman. That was it.
Wow.
They'd mix epoxy in there and it was not safe.
That's crazy.
Anyway, but yeah, and so you have the gorgeous labs and facilities we have, and just to see that it's been able to continue past what we would have even expected it to do. But what we really tried it to do, and it accomplished, being successful 2 years after we, for the founders at least, graduated, is truly amazing. And the fact that we get to, give and provide experiences for all these different engineers is truly amazing.
Where do you see yourself in the next 5 years?
Oh, man. Well, I'm actually starting work at Blue Origin in a week. So that's going to be really exciting. I'm going to be a test engineer in Texas, working on their engines. And I hope in 5 years I'm still doing that. I mean, I hope propulsion is where I want to spend my life. And whether it's going down the subject matter expert path and working in design on their engines, or going the managerial path and running teams, whether it's testing or design or specific components. I just know that I want to be a Blue Origin, and that's where I want to spend my career. But I also know that I want to work in propulsion, hands down. Doesn't matter which path goes for me.
You've gained obviously a lot of knowledge and experience through reading through your work. Where do you see the aerospace field evolving in the next 50 years?
Oh man, I think it's going to grow exponentially. I don't think people are ready for just how big aerospace is about to be again. It's like, I'm talking to a lot of people, they're thinking, so, we're just on the cusp of that second space race, and it's not with governments now, it's with companies. You have Rocket Lab, SpaceX, Blue Origin, Virgin Galactic, Firefly, there's so many, and then a million other small set companies all competing for the same space, right? Or for the same launch facilities, things like that. So it's going to be really amazing to see so many emerging technologies, because if you have that many competitors, you got to be clever and you got to stand out. And I think it's going to be really exciting to see what comes out of these companies in the next 10, 20, 30, 50 years. And then see, a lot of governments are now saying, we want to go back to the moon, we want to go to Mars, we want to send, more probes out there and figure out what's in our solar system. I don't think anyone right now, if they predict what 50 years will look like, will be right, because I think it's going to blow past their expectations, no matter how crazy.
This is Student Space Systems.
Student Space Systems is really pushing the bounds of what's possible for college rocketry organizations. If you guys like that video, please go ahead and hit that like button, smash that subscribe button, and let us know below what you'd like to see in upcoming videos.